The various landscapes that we enjoy seeing and traversing hold more information than we can possibly imagine. This is true for apparently uninteresting areas as well as the majestic. For those who seek the knowledge held within these landscapes, treasures of the past and future can be found. In this video, we will seek knowledge held within dramatic canyons that reveals not only past events, but informs us of the future. In particular, these desert canyons provides us insight into the future of Florida and other regions such as the Yucatan Peninsula of Mexico. What a beautiful fall day to go up into the foothills of the Bighorn Mountains of Wyoming. I've never been to this location, and I'm looking forward to it. These pronghorn antelope add extra enjoyment to my trip. The quiet, isolated beauty of this majestic canyon exceeds my expectations. Amazing, isn't it? The beauty of this canyon is just so inspiring to me. And that's what I do when I first come upon a landscape like this. I take some time to just enjoy the beauty of it. But it doesn't take me long to start thinking about deep time and thinking about the geologic processes that occurred to create this canyon before me. Wow! And in this case, it started about 350 million years ago with the deposition of this limestone that I'm standing on that forms this canyon, the majority of this canyon we see. And it was deposited in clear, warm ocean waters. There were reefs in these oceans and other animals like brachiopods enjoying the warm seas. But times change, and in this case, continental deposits like rivers and desert deposits came in and were deposited on top of this limestone and pushed the seawaters away. And then there were periods of new oceans coming in, and then a desert again, and rivers, etc., and the ocean again, different types of oceans, warm and cold, building up deposits on top of this limestone, built it up to some 12,000 feet. And then about 10 million years ago, there was a big, broad uplift through this whole region that uplifted everything. And this caused erosion to start to occur instead of deposition and building up erosion. Cutting down through all this 12,000 feet of rock. This sediment had turned to rock by this time, down to come right back to this limestone again. And after some 340 million years or so, this limestone got to see the light of day again. Boy, that's a long time to be in the dark, isn't it? And although I usually focus on the deep past, and most people when they think of geology and geologic history, we think of the past. You know, what happened millions of years ago? But it turns out it can give us insight into what could happen in the future as well. Deep time in the future. And in this case, this canyon and the canyon surrounding here harbor some important clues as to the future of Florida. That's right, the future of Florida. Let's learn how that could possibly be. There is something very peculiar hidden in the walls of this canyon and other canyons in the region. Our first job is to scan the walls and look for anomalous geologic features and then develop concepts that explain what we observe. This is such a fun process because you never know where the path of discovery will take you. What about these distinctive white lines we see in the cliff face? Could that be a clue? Well, they are interesting and quite distinctive, but in this case, it's not what we're looking for. Other distinctive features we notice is the red coloring that we often see near the top, and also the propensity for caves up in that area. This is close. We're getting warmer. Standing on this majestic overlook, I'm looking at a fine example of the mysterious feature we seek. There is an unusual body of red-colored rock in this area, and it seems like there is a red staining on the walls below it. Another perspective of the same layer. It runs along this line. It sure has an interesting shape, doesn't it? A closer look makes it even more interesting. What's going on? How did it form? I highlighted it here so we get a clear view of the interesting shape of this layer. With this knowledge, it's quite easy to recognize the layer in canyon walls. Note the boat for scale. Notice that the irregular shaped layer that we've been observing rests upon horizontal layers that are well behaved. And if you look carefully, you can see quite horizontal layers above this layer. Here's a very nice view of the layer. And of course, I think you're wondering, well, what does it look like when you look closely and closer? Let's take a look. Well, this is fascinating, isn't it? What do you find interesting about it? Looking at this, there's a lot to absorb in here, but I want to focus on one simple thing, and that is it looks like a lot of broken up rock to me. Also, it looks like the individual clasts have angular edges. I would call this a breccia. I think it's time to have a whiteboard discussion and discuss these breccia deposits and where we see them or how they form. And I've got a cross-sectional view here, so I think I need to draw my little tree, don't I? I'll put it right here. I'll put a nice little pine tree. It's getting closer to Christmas. Here we have the pine tree. And this represents a big cliff here, like a mountain-sized cliff, much bigger than I've shown the tree here. And on the side of the cliff, it can break up and fall, can't it? So big pieces can come off and break and form a talus slope of angular rock. So I'll put it in here. Just very angular rock of various sizes of pieces here, a deposit building this talus slope. Now, that is a breccia if it gets cemented through time and buried, which it does in the geologic record. It can form a breccia deposit. And down to this part of the sketch, which is also cross-sectional, I've drawn a heavy line, which is a fault. The arrow here showing that this side went up. It broke the rock. These layers of rock, say this blue and red layer, broke it and lifted it up. So it's, in this case, a compressional regime. And there are a lot of forces along this fault, as you might imagine, which breaks the rock up. And you can have a zone along the fault that is composed of breccia from this broken up rock. So that's another way to do it. Can you think of other ways that breccia could form? I'm thinking of glaciers. I mean, they break up a mountain and angular pieces of rock could fall on the glacier and it could deposit areas, at least, of angular rock that can form a breccia. Igneous activities, such as a volcano, as it goes off. I mean, there are a lot of forces involved there and it could break up the rock and does form breccia. Also, the intrusion of granite bodies and other types of magma that come in and break up the rock around it as it's intruded in, and it can form a breccia there. So these are all very interesting ways to do it. But you know, as I think about it, I don't think any of these processes we've discussed fits what we've seen, you know, what we observed in these canyon walls. Because we have breccia within layers of limestone. And as I think about this, I can't really make it work. And this is what's fun when you're out in the field making observations. You're immediately going through all the ways to create these breccias and trying to figure out how it occurred. So in my mind, this means that there's yet another way to create breccia. Maybe some of you have already figured that out. To learn about another breccia-forming process, we go to Mexico, near the city of Tulum on the Yucatan Peninsula. I'm going to follow my guide down this ladder, and you might guess what's in there.
A beautiful cave with crystal clear fresh water. There are countless caves like this in this region. As you would expect, sometimes the roof collapses, forming a large pit or sinkhole. Here is one of these collapsed caves or sinkholes that's mostly dry at the bottom. In Mexico, the sinkholes are called cenotes.
I'm near Tulum, Mexico, in this underground cave system that has all this beautiful water. It's considered one of the world's largest underground drainage systems. Here on the Yucatan Peninsula, there aren't any rivers or any surface drainage. It's all underground. And it's completely karsted, this karst topography. And we have a collapse here that we're able to walk down into and see this beautiful water in here.
These cenotes, caves, and passages formed and are being formed by the dissolution of limestone. Slightly acidic rainwaters are a weak carbonic acid that slowly but surely dissolves the limestone. There are so many beautiful caves and cenotes in Mexico, and many of them are interconnected. Some people think nearly all of them are interconnected. In the relatively small area I visited, scuba divers have mapped over 50 miles of connected passageways. Hopefully many of you have figured out why I've come here to Mexico to show you these beautiful cenotes and what they have to do with the breccia deposits we see in the canyon walls of Wyoming. When the ceilings and walls of caves collapse, it breaks up the rock into small pieces, relatively small pieces, and of course they're going to be very angular. Here we see a very nice example of all the broken rock on the floor of this cenote. Over time, this rock could become lithified and form a breccia. Geologists refer to this as a collapse breccia. What we have observed in Mexico could certainly explain the breccia we've seen in canyon walls. A layer of breccia within limestone deposits. It seems to fit, but does it? There are still some issues to explore, and how does this all relate to Florida and its future? I think this map could be of help. It seems that both Florida and the Yucatan have some similar features. They both have adjacent large platforms made of limestone. Could it be that they developed in the very same manner? I think a cross-section along this red line would be helpful. Let's do it on the whiteboard.
And here we are. The west side of my sketch is here. The east side is over here. This is a cross-sectional view. We're looking sideways. I could put my little tree here somewhere. But let me explain some of these features. We have basement rock with this dark line here and these check marks to represent basement rock. And all the blue with the vertical lines in here are limestones of various ages. In fact, it goes from the Cretaceous, about 145 million years ago, up through the Miocene, about 5 million years ago, was when the vast majority of this limestone was deposited. And the area right here is Florida. This wiggly line here on either side, it represents the sea level, modern day sea level. And on either side of Florida, we have these platforms out here that have been drowned. There was a rapid rise in sea level which drowned these platforms, so they're not actively being deposited upon. But they build up primarily in the Cretaceous. And this thickness here, I mean, it's a lot of limestone, 5,000 feet of limestone right here. And you easily have about half of that here sitting on top of Florida on this basement high underneath the state of Florida. And with the climate and geology of Florida, we set up for a world-class aquifer, which exists under the state of Florida. It's referred to as the Floridian Aquifer, and actually it extends to the north as well of Florida. And wow, what an aquifer it is. It's typically about 1,500 feet thick or so, and they pump about 1.5 billion gallons of water a day from it. If I drew a cross-section like this across the Yucatan Peninsula, it would look very similar to this. The geology is very similar. There is one exception. In Florida, Especially in the northern parts of Florida, there's a relatively thin veneer of siliciclastic sediments that were shed off the southern Appalachians that came out across Florida. When I say siliciclastic, I'm talking about sediment that is silica-based, like shale, mudstones, and sandstones, etc. Back to this aquifer. Now, with all this fresh water moving through these limestones, we know what happens. I mean, it's slightly acidic, it's dissolving the limestone, and we have a good setup to have karst-like features develop across the state of Florida.
Indeed, most of us are aware of the sinkhole problem in Florida and the destruction that it can cause. It seems to be in the news fairly often. As in Mexico, there are beautiful water-filled sinkholes and over 700 springs. There are several hundred terrestrial or dry caves and over 150 underwater caves, and those are just the ones that we know about. The Florida Geological Survey maintains this map, which shows all the reported incidents of subsidence. Keep in mind that this map doesn't show all the ancient scars from subsidence. This only shows the modern problems reported.
I think we need to understand karsting better, so I made this sketch. It's a cross-sectional sketch, at least the upper part is. I have my handy little tree here, and then down below is a map view looking from above down onto the ground. So coming to here, we have limestone, of course, and I've depicted various caves and passageways in here. Some of the caves have collapsed, like these, into sinkholes, and others have yet to collapse, that they could get bigger, of course, and collapse in the future. And then I have a cave at a lower level. There could be a series of these. I just put one that's full of water from top to bottom. These here might have water a third of the way up, or some of the caves could be dry, depending on where the water table is. Now, water tables can change through time, geologic time, and often that's associated with the sea level that's moving up and down through time. These solution passages can form along bedding planes within the rock, or also along vertical fractures. I might put some vertical fractures in here, near vertical. Bedding planes are horizontal, and there's more water that moves into those areas, and so you can create more solution cavities along these fractures and bedding planes, more than I've depicted here. And another thing I know you've noticed already is that I've put in red, this is critical, because these are the piles of broken up angular rock as you have collapse occur. Of course, you're going to have large amounts of it right underneath the sinkholes. But you could have very minor amounts in here. There's some collapsing, although the vast majority of it is from dissolution in here, not collapse. And now down to the map view. These circles simply represent the sinkholes where we have the collapses occur in map view, looking down. And I've put them in here relatively random in size and spacing. And that's not always true. There can be preferential patterns and sizes to these sinkholes, but I've made them random for this discussion. And wow, we've got the setup. But I'm going to ask you a very important question. If you think back to the canyon walls and what we observed, does it show this? Does this setup, this sketch, explain that? I'm not sure that it does. And furthermore, I hope you're staying patient with me here, but I hope you're starting to think, Myron, when are we going to come to the future of Florida? How does this all tie together, the canyons and karsting and all that, come to the future of Florida? Let's move on.
What we observed was a quite continuous layer of breccia. In fact, my observations of this distinctive layer in this region is that it's very laterally continuous. At a more regional scale, this breccia zone has been traced over an area of about 150 by 120 miles. The distinctive red color we see in the breccia zone comes from waters that percolated down through a red iron-rich mudstone that lies on top of the limestone shown here.
So no, this doesn't explain it. Maybe it explains it in part. In fact, it does. But it doesn't explain what we're seeing in outcrop. And I want to give you a minute to think about, well, how could this explain it? Is there a way to tweak this, so to speak? What happens through time? I think that's a good way to think about it. If we take this through time and just keep time a-rolling, what's going to happen? Well, it's pretty straightforward, isn't it? You're going to create more caves. Maybe this one will collapse. Another big cave will form here, and it'll collapse, etc. And it just keeps going. And in map view, maybe I'll collapse one here, and then here, and here, and here, etc., and just keep going and going. And you keep time a-rolling. It goes on, and this map view I've got here, all these circles and partial circles, etc., are old collapses that have collapsed down. That's where they collapsed. And of course, underneath it, you have this breccia that has developed, all the collapsed material. So you have quite a large areas of collapsed material. And that's what we see in the canyon. We don't see many places that doesn't have this collapsed breccia. And the red here are the areas that never did collapse. They're pieces that remained intact. And these can be quite tall. So, of course, everything in the blue area has dropped down relative to the red because they stay high. And some of these can get quite tall if the water table is really deep. It all makes sense. If I had these caves really deep and everything collapsed around, well, what's left could be very tall. And of course, you have the short versions too. And this is what I would call a mature karst terrain. And we have wonderful examples of that we can visit.
Who could have imagined that the simple process of dissolving limestone could produce such a beautiful terrain? This is along the Li River in China. Another beautiful example of a mature karst terrain in Papua New Guinea. Depending on such variables as climate, sea level, and time, Florida could look like any of these karst terrains. I find it rather fun to imagine these various scenarios.
Wow, what an inspiring place to be, and to think about all this history. I've really enjoyed making this video, and I hope you've enjoyed watching it. Thank you for watching.